Hello. This lecture starts Chapter 6. I'll explain the context and goal of the chapter in just a moment with an example. First, let's review just a little bit of algebra. Suppose I have a XY graph and a line here is being graphed, and I'm asking for an equation of this line. There are a couple of ways that you could go. One, you probably remember slope-intercept form, y equals mx plus b. And so m and b are specific numbers. If we can find those, we have the equation for the line. M, the slope, remember, is rise over run. And looking at the picture, if I think about going between this point and this point, the rise is actually negative. In fact, I have a fall of 2 units, and the run is positive 3 units. So the slope is negative 2/3. The y-intercept is 2, and so the equation of this line is y equals negative 2/3 x plus 2. Here's another line, the graph of a linear function. Notice something different about this example than the previous, in particular right over here. In the lower left-hand corner of this picture is where we would normally expect the origin of the coordinate axis, but notice that this is not it. The lower corner of this picture, lower left corner of this picture, is x equals 400 and y equals 500. And so in fact the y-axis is clear back over here somewhere, and the x-axis is way down here somewhere. The reason that's significant is that you can't just look here and read off the y-intercept. This is not the y-axis. What's being done here is what's typically done when a graph is made. You try to use the paper as efficiently as possible. And so since the region down here presumably was not of interest, whoever made the graph started the graph with in a position where the coordinate axes were not shown. And we've discussed that several times already in this class. It turns out for this kind of situation there's another form for the equation of a line that's perhaps more convenient than slope-intercept form, and that is called point-slope form. If I know just one point on the line, say x sub 1, y sub 1, and these will be specific numbers. So if I have specific numbers, coordinates for a point on the line, and I know the slope m, then I can use this form of the equation of a line to write down the specific equation. Let's look at this example. Let me go ahead and pick a couple of points on the line, perhaps this one and then maybe out here somewhere. And it doesn't matter exactly which points you pick. Then let's estimate the coordinates of these points. Notice find an approximation for the equation of the line. Graphical methods are approximations, and so I'm not going to be able to get an exact answer. Presumably I don't need an exact answer. So I will estimate that the coordinates of this point are 400 and 1000, while the coordinates of this point that I chose are approximately 800 and 1800. Regarding the equation of the line then, first of all, the slope, or m, is rise over run. That's change in y over change in x, remember. So I can take the 1800 minus the 1000 for the change in y, and then 800 minus 400 for the change in x. This works out to be 800 over 400, which is just 2. And now, again, I don't have to find the y-intercept, and that, in fact, that would take a little work in this problem. All I need is the coordinates of a point on the line, and I have a couple of choices. I could use either of these 2 points. If I choose, say, this point, then the equation of the line is y minus the y-coordinate of a point on the line is 1,000 equals m, that's the slope 2, times the quantity x minus, and now the x-coordinate of the same point on the line that I used before is 400. So here is an equation of the line. Maybe that's good enough depending on what I'm trying to do. If I wanted to put it in slope-intercept form, then I could multiply out on the right-hand side and get 2x minus 800. And then finally add 1,000 to both sides, and y equals 2x plus, and then negative 800 plus 1,000 is plus 200. So from the directions to the problem, this would have been an okay answer. This is an okay answer. They are the same line. Now, we'll come back to using that idea in the future. Let's go on to the main point of this chapter. It's still dealing with statistics. And in chapter 5, we dealt with data that consisted of a single list of numbers. Like maybe just this. Maybe I had just the weights of a sample of cars. And I could do things like make a histogram, make a box plot, a stem leaf plot, find the mean, find the standard deviation, find the IQR, and so on. And we did all of that. Another interesting problem to consider in statistics is relationship between 2 numerical quantities. So again, these are makes of particular cars. They all have a specified manufacturing weight, and then the EPA, the Environmental Protection Agency, tests each car that's put on the market on a standardized track under standardized conditions and comes up with an estimate of its mileage. They actually estimate the mileage for both city driving and highway driving. This happens to be the city mileage. And so now a particular car like the Chevy Camaro, has a particular weight and an associated gas mileage that goes with it. And then the question becomes, is there a relationship between the weight of a car and the gas mileage that it's likely to get? And if so, how could I describe that relationship? Can I actually write down an equation, for example, that if I knew its weight, I could use it to get the gas mileage? Let's take this data, and if we refer to the weights as the x variable and put them on the horizontal axis, and refer to the mileages as the y or dependent variable and put those on the vertical axis, then this graph shows the paired weight mileages for all of the vehicles. So for example, the Hyundai Accent has weight 2,290 pounds. That's one of the lightest cars, and gas mileage 28. So presumably the Hyundai Accent is one of these two. And just looking at the picture here, the scatter plot it's called, it's just an XY graph, your eye can already start to see some things. For example, cars with heavier weights tend to have smaller gas mileages. Hopefully that makes all the sense in the world. It takes more energy to move a heavy car around than it does to move a light car around. Notice also that this XY graph is an example of the situation we saw in the bottom example of the previous page. This is not the origin of this XY coordinate system. This graph was actually made with software, and the software chose the scale for the horizontal and the vertical axis in order to use as much of the page as possible. And so there's no point in going all the way back down to 0 on the weights. For example, there aren't any cars with weights that small. So what we would like to do now is study the relationship between weight and mileage. My eye shows me that there is some relationship. Again, heavier cars tend to get lighter mileage, tend to get smaller mileage, I should say. Heavier cars tend to get smaller mileage. And I might even want to start thinking about a line that goes through here. These points don't lie on a line, but they lie reasonably near the red line, and so maybe I could find an equation for this red line and use that equation, as I indicated earlier, to be able to predict mileages based on weights. We'll get there. Let's back off for a moment and just talk about the question of relationship, specifically linear relationship. So I only do this between two numerical variables. I could not, for example, talk about the relationship between, say, gender and weight of people in this way, because gender is not a numerical variable. It only has the values male and female. Okay, let's first talk about the direction of correlation. Two numerical variables can either have positive correlation or negative correlation. We'll say the variables have positive correlation if when one variable goes up, the other tends to also go up. And negatively correlated means when one variable goes down, the other tends to go, when one variable goes up, the other tends to go down. That is, they move in opposite directions. Let's look at some examples. Heights and weights of a group of people. So the scenario is you have a whole bunch of people and you start picking them out one at a time and weighing them and measuring their heights. And the question is, if a person is taller, say, do they tend to weigh more than the rest of the people or less? There are exceptions, of course, but all else being equal, taller people tend to weigh more than shorter people. Or you could just as easily say that heavier people tend to be taller than lighter people. And so the correlation between heights and weights is positive. How about correlation between family income and number of children, at least in U.S. families? So do wealthier families tend to have more children or less children than poorer families? And you have to know something about sociology and family structure in America. It turns out that the correlation is negative. Wealthier families tend to have fewer children than families that are not as wealthy. And actually this holds on a worldwide basis as well. If you think about it, countries where the per capita income is smallest also tend to have very high birth rates. And conversely, countries that have fairly high per capita income, so the United States, Western Europe, Japan, countries like that, tend to have fairly small families. And there are sociological reasons perhaps for that. One explanation might be that parents who have high incomes because they're very dedicated to their careers. Both parents are probably working, and those may be people who choose not to have very many children because they don't have time, or they don't believe that they can be good parents to large numbers of children. How about SAT scores and college grades? So do students with high SAT scores tend to get high grades or low grades? The answer is they tend to get high grades, and the correlation between these two variables is positive. And this is the reason that the SAT and ACT exist at all. They're used as predictors. Colleges use them as predictors for success in college. And so colleges are more likely to admit students with high SAT scores, reasoning that they're more likely to do well in college. And weights and gas mileages of a number of cars, we already said that those are negatively correlated. Let's think of some examples. I want to talk about variables with who are correlated with GPA. And first, examples of numerical variables which are positively correlated with GPA. So maybe you can think of some. Here are some examples. High school grades. So here I'm thinking about college GPA, by the way. So students who tended to get good grades in high school also tend to get good grades in college. So I could think about a high school GPA. Another thing I could think about is study time. This is a little tricky because it's certainly not true in every case. But all else being equal, students who study a lot probably tend to do better in terms of grades in college. How about an example like father's GPA? So if your dad went to college or in high school, say, if your dad tended to do well in school in terms of grades, you will tend to do well in school in terms of grades. This is a well-studied situation in educational research and sociology. The argument probably goes that parents who get good grades in school themselves value education and are skilled in knowing how to study, and then they tend to pass those values and techniques on to their own children. Something else that's positively correlated with GPA is IQ. So some of these you have control over if you're looking to raise your GPA. Study time, for example, is something that you definitely have control over now, and high school grades is something that you had control over in the past. Other things like father's GPA or mother's GPA and IQ, you really have little or no control over. Is that fair, then, that it's positively correlated with GPA? Maybe not. Doesn't seem like it, but that's kind of the way that life is sometimes. How about variables that are negatively correlated with GPA? I can think of one: time spent playing video games. Big problem for some college students. Spend a lot of time gaming and then don't have time to study, and GPA suffers. So similarly, something like party time. You could think about things like sleep time. Do you think that students who spend more time sleeping tend to get lower grades or higher grades? And the reason this is a little tricky, you could argue both ways. On the one hand, students who sleep a lot are probably more alert and healthier, and you might think that they got better grades. On the other hand, students who sleep too much may not spend much time getting out of bed and going to class and so on. So sometimes it's a little tricky to predict because there may be several effects going on that are pulling in opposite directions. Okay, let's get more specific. We talked about positive and negative correlation. Now let's talk about strength of correlation. So instead of just saying positive or negative, I'm going to say things like strong negative, moderate negative, weak negative, and likewise for positive correlations. So here are 6 scatter plot pictures, and let's go through them one at a time and classify them by positive negative correlation and strength of correlation. It's actually easiest to start at the bottom, and so let's start in the lower right hand corner. These are negatively correlated and the relationship is quite strong. They are clustered along a line pretty tightly, so this is an example of strong negative correlation. In the lower left is another example of fairly strong correlation. This one is positive. It's not quite as strong as the one on the lower right. The dots are spread out a little more. If we move to the middle right, here might be something we could call moderate, and then the shape of the dots shows a downward trend, so negative correlation. On the center left is an example of moderate positive correlation. And now we move up to the upper right. Your eye has to think about this one for a little bit. Hopefully you'll agree that this is negative correlation, but it's not strong negative correlation. In fact, it's really pretty weak. And in the upper left is a picture that actually shows no correlation. This is basically a circular pattern. It's like a shotgun picture. You stand at the back of the room and shoot a shotgun at the bulletin board or something, and these pellets just spread out in more or less a random circular pattern. So, those are adjectives that describe the strength of correlation. Let's continue to get more specific and actually talk about a number. So there is something called a linear correlation coefficient. It's also known as the Pearson R. And it describes correlations on the following scale. The Pearson R, or the linear correlation coefficient, can be any number between -1 and +1. And we interpret the values as follows. So something with R equals, say, -0.8. This would be an example of a strong negative correlation. If R turns out to be 0, there's no correlation. If R turned out to be something like 0.3, we could call that weak positive correlation, and so on. So to summarize, if the R number is positive, then the correlation is positive, and if R is negative, the correlation is negative. And then the strength is weakest in the middle, no correlation, and then as I get closer to -1 or +1, the correlation gets stronger and stronger, either negative or positive, depending on which direction I'm going. Let me come back to the pictures then, because these were computer generated pictures. It turns out that we know exactly what the R values are. And so there's no way you could know these values exactly from the pictures. What I want to do is give them to you so you can get a feel for what a scatter plot looks like for various values of R. This is R equals 0. So no correlation, a scatter plot tends to look like this. Here's a case where R equals -0.3, so weak negative correlation. Here is R equals +0.5, R equals -0.7, R equals +0.9, and R equals -0.99. And you see this is getting very close to -1, and so we have very strong negative correlation in this picture. How is the Pearson R computed? Well, it can be done algebraically. There's a fraction illustrated here, and in the numerator I have to do things like take a data value, subtract off its mean, and divide by its standard deviation. That's in the list of x values. Then I do the same thing in the list of y values. Take a data value, subtract off the mean of that list, divide by the standard deviation of the y values. I multiply those two quantities together, and that gets me one term, and this is the summation symbol. So for each of the data points, like in this list with the car weights and mileages, it would be to take a data value and x value, subtract off the mean of these numbers and divide by their standard deviation. Do the same thing for the y's, and then I multiply the two transformed quantities that I just described and keep adding together as I go down through the data values. That's a lot of work. It's almost undoable by hand. And so here's an example showing how to do it using Excel. And in the homework and on tests and so on, you're certainly free to use Excel. In fact, that's pretty much what I have in mind. So let me demonstrate Excel finding a correlation coefficient or an R value. If I bring up Excel, I've already entered the weights and mileages in Excel, with the first row being used for headers to tell what variable is in each column. And now perhaps you've already done this from an earlier assignment, but I want to install the data analysis tool pack. So if I go to the Windows button here, or the Office button, or on Office 2010 the File menu, and then choose Excel Options and Add-ins, this is where we found Solver, remember, and I really want now the Analysis Tool Pack. So if Analysis Tool Pack is down here somewhere, go ahead and click on it and then hit Go. And then check Analysis Tool Pack here. I actually have Solver still turned on, that's okay, but I want to check Analysis Tool Pack here and click OK. When I do that and go to here are the tabs up here, and I go to the Data tab, now I should have a Data Analysis button over here on the Analysis tab. So if I want to find the correlation coefficient of this list of weights and mileages, choose Data Analysis. And now there are a list of statistical commands that you can use this analysis tool pack for. Choose Correlation, click OK, and that brings up a dialog box which you need to fill in, just like for Solver. So input range, the data values are stored here. So what I'm going to do is click and hold down and then drag until I've covered the entire XY data list and release. Click, hold, drag. My data does in this case have labels in the first row. By the way, in order to do the entry that way, notice that the X values and the Y values had to be in adjacent columns, side by side, so I could drag across both of them at the same time. Now, regarding the output, let me click Output Range and click in this box, and it's just saying where do you want the answer to appear. So anywhere off to the side here would be fine. I'll click cell D1 and then click OK. And here it is giving the correlation coefficient between the variables. So the correlation between weight and weight is actually 1. I mean, those are perfectly related. They're the same variable. The more interesting thing that I was looking for, the correlation between weight and gas mileage, now I see is negative 0.87 approximately. And so without too much work, if you have the data in Excel, you can get the Pearson R, or the linear correlation coefficient, between those two variables. Okay, let's go back to the worksheet and do one more thing. I want to throw out some cautions here. Excel makes finding the Pearson R so easy that some people may start to misuse the Pearson R. Remember, there's a saying in dealing with computers, computer programming in particular, garbage in, garbage out. If the programmer makes a mistake, then no matter what you do, the answer is going to be flat out wrong. In statistics, the same thing applies. If you use a particular statistical technique without thinking about what goes into the background and how it's intended to be used, then you can use a computer and get answers that really don't mean what you think they do. So here are some cautions about using the correlation coefficient. Let's look at an example. Here is outdoor temperature in degrees Fahrenheit over a number of months. And here's the utility bill for a particular corporation. This is probably some large building using $24,000 worth of heating and cooling, and then $14,000 in the next month and $9,000 in the next month, and so on. If I make a graph of that, it looks like this. So here's temperature along the x-axis and utilities paid in thousands of dollars along the y-axis. And you see this U-shaped graph. Why is the graph shaped that way? Well, if you think about it, when the temperature is low, say 10 or 20 degrees Fahrenheit, you're using quite a bit of energy for heating. But on the other hand, when you get out here and the temperature is quite high, 95, 100, 105, then you're using, again, a lot of energy, and this time for cooling. When the temperature is like 60 or 70 degrees, where we're perfectly tend to be comfortable, then we don't have to heat or cool very much, and so the utility bill is very small. But the point for the example is, what is the approximate value of the Pearson R? So I look at this scatter plot and think back in my mind as to what these scatter plots look like and what R values went with them. In particular, I start thinking, well, is R negative here or positive? The data points seem to be going down, so R might be negative, but then they go back up again, so R might be positive. And you can't say both, or you can't say it's first negative and then positive. This is an overall data set. So in fact, R turns out to be approximately 0. And then a conclusion that you might jump to would be, well, if R is 0, then there's little correlation, almost no correlation between these variables, so they're not related at all. But we just argued that they are definitely related. The temperature definitely makes a difference in your utility bill. If it's very cold or it's very hot, you're going to pay a lot of utilities. So knowing the temperature tells you something about the utility bill. What went wrong? Why is R approximately 0? Why doesn't it capture information here? And the answer is that R only measures the strength of linear relationship. The graph, R is measuring how closely the graph clings to or follows a line. These points follow a curve, a parabola in fact, but in terms of a linear relationship they're not very related, and so R is small in size. Here's another caution. Let's look at a case study or a thought problem here. Is the correlation between geographic density of crimes and geographic density of churches positive or negative? So let me pick Grant County, for example, and divide Grant County into a grid like this. And then suppose I go through each of these individual areas, maybe these are square mile sections, and I start looking in police records and finding out where crimes were committed, how many crimes were committed per square mile. And I also drive around and look at the churches and count churches per square mile. So I then can think about each of these square miles as a data point, and then it has an x coordinate, the number of crimes, and a y coordinate, the number of churches. And so question, do you tend to have more crime or less crime in areas where there are a lot of churches? That's an interesting question to think about. I mean, presumably churches are filled with people who are Christians, and maybe some people who aren't but are visiting churches, but pastors and parishioners try to tell their congregants that you should play by the rules and not commit crime. So you would think that lots of churches would lead to lower crime. In fact, it's exactly the opposite. The correlation is positive. In fact, the correlation is strongly positive. wherever you find a lot of churches, you're going to tend to find a lot of crime. Oh, well, that's not so good. That might lead somebody to think that the answer to solving our crime problem would be to go out, find churches, burn them down, and then there won't be very many churches there, and then there won't tend to be very much crime there. Well, that seems kind of silly. How could we possibly think we're going to reduce crimes by burning down churches? The reason that thought process is faulty is that there is a so-called lurking variable in the population. Who commits crimes? People. Who build churches? People. So why is this correlation positive? Well, there are a lot of crimes as well as a lot of churches in areas that are highly populated. And there are few crimes and not many churches in areas that are sparsely populated. And so population is really controlling both number of crimes and number of churches. And if we don't think this through, we might look at this relationship and say, oh, churches are causing crime, or maybe crime is causing churches to be built or something. And nothing of the sort. It's population that's going on in the background. Moral of the story, correlation is not necessarily cause and effect. Just because you see two variables are highly correlated doesn't necessarily mean that one of those variables is causing the other. Here's another example. A study published in a very famous medical journal found that children who were breastfed as infants were less likely to be obese later in childhood. How could we explain this positive correlation? Well, one explanation might be that there is some nutrient or chemical in hormone in breast milk that would cause the baby's metabolism to somehow adjust and become more healthy. And then years later, even in, say, early teens, that's still helping the child to metabolize nutrients better and perhaps stay healthier and not gain weight. There's probably a better explanation, and that would go something like this: that mothers who breastfeed tend to be more health conscious. And so after their children are eating regular food, their mother probably is tending to choose healthier diets for them. So maybe giving the children lots of fruits and vegetables and so on. But then that in turn, if you have a good diet, you tend to have less risk of obesity. And so in this case, the mother, or the health consciousness of the mother is contributing to both likelihood of breastfeeding and healthy weight. So it is possible that breast milk may physically have something that contributes to lower body weight later in childhood. More likely explanation is the attitude and decisions made by the mother. Again, correlation then is not necessarily cause and effect. And we'll stop there. Thank you.